All right, so let's take a look at this problem number 17. It's got four parts to it, but we'll see that parts A and B are very similar and parts C and D are very similar. So we've been studying functions, and we know that you can use two functions to create a new function through various operations. The normal operations that we see in math in elementary school, continue through high school, is addition, subtraction, multiplication, and division. But when you get to a point in algebra that you begin to study functions, there's another operation called function composition that you can also combine two functions together. But here in this problem, we're just doing addition, subtraction, and I think division, or maybe addition, multiplication, division. Let's take a look at these and see what we have here. So we're given two functions, f and g, and we're asked to create a new function. And rather than calling this new function something like h, they call it, the title is f plus g. And so this is not multiplication, this is function notation. And even though we're going to sit here and think of this as taking f of x and then adding g of x, you know, again, a student is going to look at that and think, well, you just distributed that x to both terms, but I'm telling you, it is not multiplication. It's just notation for functions of how to build a new function. So now, through substitution, I'm going to take this first function, that first term, and add the second function. So when I look at x over x plus 2, I'm going to add it to this 3x minus 1 over x minus 1. Now, they expect me, if I'm given two fractions, to add them together to just have a single fraction. So whenever I'm adding or subtracting fractions, I need a common denominator. So it's a common technique to multiply these terms by the number 1, but to be clever in how we write the number 1. I'm going to write the number 1 as a fraction. And if I want this fraction to reduce to the value of 1, the numerator and denominator have to be the same. And I look over here, I see an x plus 2, and boy, I wish that right next to it in the denominator was an x minus 1. So I'm going to put x minus 1, and like I say, I need the numerator and denominator to be the same. So I'm not changing the value of this first term when I multiply it by 1. It'll look different. It's like looking at 1/2 and recognizing that that's the same number as 5 over 10. Because I can multiply by the number 1, 5 over 5. 5 times 1 is 5, and 5 times 2 is 10. I did not change the value of this 1/2. 1/2 is equal to 5 over 10. They look different, but they're the same value. That's the idea that I'm doing here with this variable x. All right, so in the second term, I have the factor of x minus 1, but I'm missing this other factor of x plus 2. So again, it's the same idea. I'm going to multiply by the number 1, but this time I'm going to write 1 as x plus 2 over x plus 2. So now, when you multiply fractions, it's so much easier than when you add or subtract, because when you multiply, you just multiply straight across the numerator and straight across the denominator. So the denominator in this first fraction is x plus 2 times x minus 1. And that's the same denominator you have over here, except that the order of multiplication is different. But we know that the order of multiplication doesn't matter, that 2 times 3 is the same number as 3 times 2. And they call that property commutative property. Not every operation is commutative. Subtract 2 minus 3 is not the same thing as 3 minus 2. Now, multiplication and addition are commutative, but subtraction and division are not commutative. All right, so what this is telling me here, I have the same denominator, and these two fractions can be written as a single fraction, and it's going to have a denominator of x plus 2 times x minus 1. Now, my numerator, I'm just going to add these two numerators together. So I'm going to have x times x minus 1, and I'm going to have 3x minus 1 times x plus 2. Now, all the time in algebra, when you have these ratios, when you have this rational functions, it is to our advantage to have this denominator written in factored form. So I'm not going to create a table to multiply these two binomials together. We'll see, especially in our next skill packet, that it's an extreme advantage to have this factored. I don't know if you can hear that new bell, that different sounding bell. All right, but here in the numerator, well, it's easy to distribute the x through x minus 1. I'm just going to have x squared minus x. And if you're not good at multiplying binomials, a nice way to multiply these binomials is in the form of a table. I mean, you don't have to do this, especially if you do it often enough, you begin to just be able to look at it and see what it is. You know, to see that I'm going to get 3x squared plus 5x minus 2. But here, 3x times x is 3x squared. 6x, because 2 times 3x, minus x. I'll put a minus 1x just to emphasize that that diagonal is like terms, and then positive 2 times a negative 1. So you can see that 6x minus 1x, that's how I got 5x. So this table helps me to get this trinomial, to get that binomial times a binomial to get these three terms. And now I'll scan that numerator and see what like terms there are. 1x squared and 3x squared, 4x squared. And again, maybe people like putting a 1 in front of there. 5x take away 1x, 4x, and then I just have this minus 2. And I'm going to leave that denominator in factored form. So there's my final answer for part A. And most of this work is going to carry over, well, a lot of this work is going to carry over to part B. So let's see if I can save a little bit of time to copy and paste. Well, there it is. And let's take away the A and come here with the B. So in part B, if I want this new function f minus g, then instead of adding f and g together, I'm going to subtract them. So it's still, to add or subtract two fractions, you need a common denominator. So I'm still going to have this first term and the second term being the same. But what's going to change here is this addition right there. And I'm going to put parentheses around this, change this addition to subtraction, and I'm going to erase the rest of this so that I want to be careful that I don't edit too much. I have to be able to read my own handwriting. All right. So if I haven't made any silly type of a mistake, this time, let's distribute that minus sign through there so that we don't make any kind of mistake. Now, again, I'm going to leave the denominator in factored form. All right, so let's move this up a little bit, shrink it up, give us some room. It's a nice thing about this software. So 1x squared take away 3x squared gives me a negative 2x squared. This negative 1x and minus 5x gives me a negative 6x. And I have plus 2, and I'm going to leave that denominator in factored form. So there's my answer for part B. Now, let's take a look here at part C. this is function notation. This is not division. Instead of giving this title of this new function a letter like H or P or R, they're just saying, hey, I'll give it a title, I'll give it a name so that people can understand how it was constructed, how it was built. So I'll come in and often think of this as, well, this means that I'm taking the function f of x and I'm dividing it by g of x. Okay. Well, since f and g are both rational functions, they're both fractions themselves, this is a little bit intimidating to students because the numerator is a fraction, x over x plus 2, and the denominator is also a fraction, 3x minus 1 over x minus 1. So when you have a fraction within a fraction, they often refer to this as a complex fraction. And remember that this fraction bar, if you have 10 over 2, that's just another notation for division of 10 divided by 2, you know. And hopefully back in your elementary school days, you remember that division is the same thing as multiplying by the reciprocal. That if you have this divisor 2 and you write it as a fraction 2 over 1, I can rewrite this 10 divided by 2 as 10 times 1/2. And I get the correct answer, that 10 divided by 2 is 5, or 10 times 1/2 is 5. Well, if it's good for numbers, then it needs to be good for variables in our algebra. So if this fraction bar here represents division, I'm going to take this x over x plus 2, and I'm going to change this division to multiplication. If I take the reciprocal of this divisor, if I flip this x minus 1 now becomes the numerator, and this is 3x minus 1. So it's, it looks intimidating, but honestly, to just flip a fraction like that is a lot easier than addition or subtraction, than going in and looking at something and finding common denominators. Multiplication and division of fractions is much easier than addition and subtraction, because now with multiplication we just multiply straight across. So these two fractions combine to give me a single fraction. The numerator is just this numerator times the other numerator, and the same with the denominators. You just multiply them together. And just as in the previous parts, we're going to leave this denominator in factored form. So the numerator will distribute x squared minus x over this x plus 2. So here's my new function that I get when I divide f divided by g. That the function f of x divided by g of x creates this new function. And if you want to, you could rename it h of x, or you could keep that name f over g. So there's my final answer for part C. Part D is going to be the reciprocal of this answer. Think about this, like I say, that we've done most of the work. If this guy right here is f of x divided by g of x, and if in part D I want g of x divided by f of x, well, I guess this technically isn't the numerator. You can't sit here and equate. When I say that this ratio is equal to this ratio, I'm not necessarily saying that this numerator is equal to f of x, because obviously that f of x was a fraction, and this numerator is not a fraction. But what I'm saying is that this ratio is the same as this ratio, and if I flip the right-hand side, if I take the reciprocal of the right-hand side, I can take the reciprocal of the left-hand side, and I can say that this guy is my x plus 2 times x minus 1, which is the denominator right here, and this numerator, x times x minus 1, x times x minus 1, and I'm going to leave that denominator in factored form. I'm going to multiply, and you can do it in the form of a table over here if you need to, x squared plus x minus 2 all over x times x minus 1. That's using my work that I did in C to get D. Now, if you didn't think of that, suppose that you were taking a test and you just didn't think to use that previous answer, let's prove to you that this is the correct answer that we would get if we worked it out just like we did in part C. So if I recognize that this is a complex fraction, if I have 3x minus 1 divided by x minus 1, and f of x is x over x plus 2, since this fraction bar represents division, I can change it to multiplication. If I take the reciprocal of my divisor, if I flip this bottom fraction, x plus 2 over x, and I think you're beginning to see that we're going to get the same answer, right? Because now, when you multiply fractions together, you just multiply straight across. So I've got this binomial, 3x minus 1 times x plus 2. Because these two fractions, I'm going to create just a single fraction. I'm going to take x minus 1 times x, and it doesn't matter the order that I write that multiplication. Over here, if I came over and did a table, I would get 3x squared plus 5x minus 2 over, how come I didn't get the right answer, the same answer as before? Maybe I made a mistake over there, darn it. Well, I don't want to redo this whole video. Okay, I should have been able to take the reciprocal. The reciprocal of this answer should be that 3x minus 1, x plus 2. That, yeah, 3x minus 1, x plus 2, that denominator is now my numerator. And this denominator was my new x times x minus 1. Yeah, so y oh, I didn't flip it. When I was sitting there, I just wrote this again, didn't I? No, I did have that. Maybe I multiplied that together wrong. When I multiplied this together, that I should have had 3x squared plus 5x minus 2. So the concept was right. Unfortunately, I hope I didn't confuse you in my algebra, because look, that here I'm getting that answer that I should have gotten if I take the reciprocal of this guy. I don't think I'll have time to redo all of this video. Maybe I'll try to edit it